Hi students, in this video I will go through the derivation of why or how the centroid is one-third away from any given base, or one-third of the median away from any given base, and two-thirds away from any given vertex. Um, we've definitely gone through the concepts related to this in class, but we never gone through as to why or how this is actually possible. It was sort of just given to you. So in this video, um, based on that enrichment assignment that I gave you, I will try to go through that derivation, and you can definitely check your work that you had put in going through this process along with me. At any point in time, if you feel like you need to pause the video just to have some of the information that I'm telling you just sink in, please do so. Pause and look at some of the computations that I go through, and just reflect to see whether or not any things that I've done makes any sense, or any things that you've done is consistent with what I am saying. And you should definitely bring that up to office hours if you have any questions. Anyway, let's get started. So, in any proof or in any kind of derivation, this is the part that I love about math so much, because it's all about a thought process. This is all a thought experiment. Okay, so what we talk about here, okay, has to be applicable in any situation. So we start off with a triangle, like I have drawn here, okay? And the given information that you're starting off with is we have to have an understanding of what a median is, okay? So a median is a line drawn from any vertex. Give me a second here. So the median is a line drawn from any vertex. So a vertex is the corner of a triangle, and the line drawn to any vertex from vertex to the opposite base, such that the line that you draw, okay, in this case that line highlighted in yellow, it bisects the opposite side. The opposite side has to be bisected. And the very definition of what it means to bisect something is to break something into two equal parts. Okay, and if we do this two more times, you're going to see that the medians, they intersect. The intersection of those medians, form what's called the centroid. And this point is what we are going to investigate. Why is this point one-third away from the base, and two-thirds away from the vertex? One-third of a median away from a given base, and two-thirds away from a vertex. So to start off, okay, like I said before, math is all a thought experiment. That's, in my opinion, what makes math so beautiful, because we can create so many things just from our minds. And that could be said about anything, any discipline. So any true philosopher, or any true individual who has invested a ton of time in a certain discipline will share very similar feelings about the subject that they're passionate about. So so in any derivation, right, one would never want to create more chaos than really needed, because right now, if you think about this, right, like, where do you even begin? How do you even go through proving why the centroid is one-third away from any one-third of a median away from a base, and two-thirds of a median away from any vertex? Like, where do you even start, right? It's the same kind of phenomenon that a person gets, in writing. They're sitting there, and a student, or perhaps maybe an adult, okay, that who's a writer, and they get writer's block. Well, the same thing goes with math derivations. it does require some inspiration, and it does require a little bit of insight about the subject, but there is a lot of creativity that's involved. Okay, and the creativity is it has to do with how efficient you are in naming things, how efficient you are in categorizing things to eliminate as many variations as you can, to eliminate as many variables as you can. So the proof that I'm about to do here, okay, is I can't say that it's the most efficient, or at least this is the approach that I thought of as most obvious. Okay, I am sure that if you Google some other approach, okay, it will be maybe a lot simpler than what I had gone through. But at least what I'm doing here, I feel like it is parallel to some of the things that you guys have seen in Algebra 1 related to a lot of the algebra, okay, that you guys have studied. So this is the approach that I'm taking it. So the way that I thought of this was, let's plot this triangle on a grid, okay? And there are so many ways that you can plot, a triangle on a grid. You can plot a triangle, somewhere in the first axis, second axis, first quadrant, second quadrant, third quadrant, or fourth quadrant, right? You can have the vertices of the triangle sprawled out all over the entire grid. But if you do that, let's just think about this, right? If you have the vertices sprawled out all over the coordinate grid, and each coordinate has two variables. It has an x coordinate and a y coordinate. That creates 6 different variations in things, right? And what I was saying before, math is very creative, and you really do need to have some efficient way of thinking about things. This is a very good example of that, right? So how can I plot a triangle on the coordinate grid so that I can possibly decrease the number of variables that I am working with? And if you think about this, right, probably the most efficient way, okay, is to place the coordinates, place the vertices of the triangles on the x and y axes. And if you do that, and I'm going to slowly chip away at some of the things that I'm covering up here, and if you do that, right, if you do that, we can then see that some of the coordinates, some of the x and y coordinates can be eliminated, right? So this was done on purpose. I labeled this coordinate over here. I labeled this coordinate on the right, a comma 0. I labeled this coordinate over here, b comma 0, and this coordinate up here, 0 comma c. Why am I doing that? Well, that's because it is always way easier to work with numbers that are 0 and 1, right? Just because 0 is an additive identity and 1 is a multiplicative identity, anytime that you can work with either 0 or 1, you should definitely go with it, okay? And by doing this, okay, I essentially eliminated 3 different variables. I've eliminated 2 y coordinates and 1 x coordinate. So now I only have to worry about quantities of a, b, and c, okay? So, and the other thing I want to start with, okay, these 3 numbers, okay, these 3 coordinates that I've highlighted in pink right now, these, even though they're variables, we're going to treat them as knowns, okay? So values of a, b, and c are quote-unquote knowns. I mean, even though we don't have a specific value for A, B, or C, we're still calling them knowns. And that is because this triangle has to exist somewhere. Excuse me. This triangle has to exist somewhere. In order for the triangle to exist, in order for this triangle to exist, values for A, B, and C must exist. So that means we have to start off with values of a, b, and c as some known value. If you're having difficulty digesting what I just said, just think about it like this, okay? We are trying to prove something, and so what we're proving has to be applicable for any triangle. So to make this proof applicable to quote unquote any triangle, we have to create this so-called any triangle. This so-called any triangle will have vertices of b comma 0, a comma 0, and 0 comma c. So we can vary up values of a, values of b, and values of c, and then we can create all kinds of triangles out of this. This triangle can then turn into an obtuse triangle, an acute triangle, an equilateral triangle, a right triangle, any triangle you'd like, if we vary the values of a, b, and c. But again, it is important that you understand that these things, a, b, and c, okay, these are our known values that we're starting with, okay, because this is declaring the triangle on the coordinate grid, okay, so this is important. Okay, so once we have that established, we should also recognize what our final answer should look like. Our final answer at the end should involve quantities of a, b, and c, okay. So let's just go through it, okay? So again, we're operating with a, b, and c as our known values, and the centroid is formed by the intersection of medians. So therefore, it would be important for us to figure out those midpoints. So the midpoints on the three sides of the triangle can be calculated using the midpoint formula. Again, if you have difficulty following why those 3 points are the midpoints, please pause the video and go through and verify for yourself that those 3 coordinates are indeed the midpoints of the 3 sides of the triangle. Okay? So again, you're wondering, like, well, where do we go from here, Mr. Chan? Like, this looks very awkward. There's so many letters everywhere. Like, what do we do with this? Let's just keep our goal in mind. Our goal is to figure out or to determine that the centroid is 1/3 median away from the base and 2/3 away from the vertex, which means it would be helpful for us to determine the coordinate of the vertex, right? So how do we find the coordinate of the vertex, right? The coordinate of the vertex, once we find it, has to be in terms of a, b, and c. But the question is, how do we find this out? If you recall from Algebra 1, right? Wait, anytime we have 2 more lines coming together to a single point, that is a point of intersection. How did we, or how did you, find a point of intersection on a coordinate grid in the past, right? If you're thinking a systems of equation, you are definitely on the right track. So in order for us to find the point of intersection, we will then need the equations to represent the 3 medians. So in order for us to do that, okay, just recall from Algebra 1, we need to have 2 things. We need a slope and we need a point. Lucky for us, we found our points, okay? We have 1 point, but we need a slope, okay? We have 1 point, but we need a slope. We have another point, but we need a slope. So let's do that, okay? So we're going to find out what the slope is for the line passing through a comma 0, okay? So in order for us to do this, we're going to apply change in y over change in x. So change in y over change in x. If we do that, we'll end up with something like this. And again, if you need to pause a video to verify for yourself that the computation here is accurate, please do so. So now I have the slope for A. While I'm at it, since I'm figuring out slopes, so let's figure it out for all 3 medians. I want to do it for B and as well as for C. So I'm going to zoom right there, okay, so that you can see everything. So again, if at any point you need to pause the video to verify whether the computation here is accurate or not, okay, please do that. But again, all I did was I applied change in y over change in x. Now that we have the three slopes, we are going to try and write out the equation of the line. I do not recommend using slope-intercept form to write the equation of a line, just because I can already tell that the y-intercept for the medians, it's not going to be nice, with the exception of like maybe the one line that passes through 0, c. So I will recommend writing the equation of a line in point-slope form. If you need to recall what point-slope form is, please pause the video and look that up, okay? Or actually, I'll just tell you right here. So point-slope form of a line looks something like this. It looks like y minus y1 is equal to m times x minus x1. Okay? So what we're going to do is we're going to take the slope at a, the slope that passes through a comma 0, and we are going to find out what that equation is. So the slope that passes through a comma 0, okay, the slope that passes through a comma 0, the slope, the equation of a line that passes through a comma 0 is going to look something like this, okay? Again, I take the slope of that line, which is c over b minus 2a. So again, I take this quantity, I take this quantity right here. That's our slope. I plugged it in over here. And I also recognize that the line passes through this guy, right? So therefore, I place in the x-coordinate, which is b over 2, and the y-coordinate, which is c over 2. So I have my equation. Okay, so that's the equation for the median that passes through a comma 0. I will then repeat this, okay, for the other two medians. The other two medians, one will pass through 0 comma c, and the other one will pass through 0 comma b. But again, I will go ahead and treat those medians in the same manner, and I will then achieve those three lines. So these are the three lines. So these three equations, okay, are the equations for the medians of this known triangle. And what I'm going to do with this, what I will do with this, okay, is I'm going to find the point of intersection. So the point of intersection can be found by equating the two lines with one another. And once I equate the two lines with one another, I can then solve for the x-coordinate. And when I solve for the x-coordinate, I can then solve for the y-coordinate. I can then perform a substitution and place it into that last equation. So that is the approach that I'm going to take here, right? I'm going to take the first two equations that I found, I'm going to equate them to one another, and then I'm going to substitute the x-coordinate into that third equation. So let's see what happens. All right. So I isolated y for both equations. Okay. So again, c over b minus 2a times x minus b over 2 is equal to c over a minus 2b times x minus a over 2. Okay? So I take those two equations, and they were equated to one another. Okay? And what we do from here, we're going to try to solve for the x-coordinate. Okay? When we solve for the x-coordinate, that x-coordinate will be the x-coordinate of the centroid. So you look at this, and it looks like an algebraic mess. And you're right, it is kind of an algebraic mess, but we have to muscle through this, okay? So how do we go about that? I look at this, okay, and I see there's some simplification that I can do over here. Whoops. There's some simplification that I can do over here involving x minus b over 2a. Involving x minus b over 2. And over here I have x minus a over 2. I can create common denominators so that I can create one giant fraction. You may be wondering, like, how is that even useful? Well, that's because I can then turn two fractions into one expression, into one term. I didn't do anything different in that last step. That's okay. The next step, there will be different. It will be different. So I created common denominators. Okay, so if I do that, create common denominators here, 2 times x minus b all over 2b minus 4a, right? If you need to pause a moment to verify whether or not what I did here is correct, please do so, or you can come to talk to me in office hours on why or how that's the case. And the same thing could be said about on the right-hand side. If I create common denominators and then combine the fractions together, this is the end result of what I will get. Then the next step, remember the goal is to isolate what x is. So even though this looks really complicated, we're going to cross multiply. And if I cross multiply, I end up with this really nasty looking thing, which is okay. Because again, our end goal, remember, let's just keep this in mind, that we need to find out what that unknown x is. That x will give us the x coordinate of the centroid. From here, we're going to go through a little bit of math, a little bit of algebra, and our goal is to figure out what x is, to isolate what x is. So we're going to, and the only way that we can do that is to get x out of the set of parentheses there. So the only way is to distribute. So I'm going to distribute, I'm going to FOIL the expressions on the left and the expressions on the right. And I'm going to further isolate by bringing everything that has x's over to one side and everything else that doesn't onto the other. If you need to pause a video to verify and check what I am doing here makes sense or is accurate, please do so. So again, all I did in the last step was I brought this to the left, and then I brought this to the right. Okay, that's all I did. And then from there, okay, I noticed that the expression on the left, okay, there are common factors, okay, in the expression on the left. So what am I going to do? Well, I am going to factor that out. I'm going to erase all this. I want to factor out a 2x. And again, if you need to pause the video just to verify whether or not this is accurate, please do that. Inside the bracket on the left, you're going to notice that there are like terms that we can combine together. So from here, you can see now the expression is boiling down. It's getting simpler. Okay, we can isolate x in the next 2-3 steps. On the right-hand side, again, we can distribute. Combining like terms, I get 4a squared minus 4b squared. If you recall from Algebra 1, 4a squared minus 4b squared, wait a minute, isn't that a difference of squares, right? And that can also be factored, right, to become 2a plus b and 2a plus 2b and 2a minus 2b. But before I even did that, if you look at the expression on the left here, I see that there's a 12, and there's 4 and 4, right? There's a common factor of 4. We can divide both sides by 3. So I did all that in one step. I factored the difference of squares, and I also factored the common factor of 4 from both sides. And what will happen then, I'll end up with an expression that looks like this. 3x is equal to a plus b. And then finally, the x-coordinate of a triangle will end up being this. So x is equal to a plus b over 3. This is our centroid. This is the x-coordinate of the centroid. This will not be complete, okay, until we found the y-coordinate of the centroid. So to do that, we're going to take this x-coordinate, and I'm going to substitute it into that third equation that we found. Right, the equation for the third median, which passes through 0, c. And if I take the x-coordinate of the centroid and substitute it into this equation, we'll end up with something very, very nice. And then finally, we'll end up with y is equal to c over 3. So the y-coordinate of the centroid will be c over 3, and the x-coordinate will be a plus b over 3. Very simple. Okay, so now that we have the x and y coordinates in terms of our quote-unquote knowns, we need to now determine whether this coordinate is indeed 1/3 away from a base and 2/3 away from the vertex. So what I decided to do was I'm going to select, for demonstration, these two coordinates here. So a plus b over 2, 0, and 0, c, remember where that was, okay? So this is the line right down the middle, this guy right here. So I'm going to verify whether or not the centroid is indeed 1/3 away from the base and 2/3 away from that vertex. So let's take a look. In order for us to do this, it would make sense for us to figure out what is the length of the median, right? So to find the length of the median, I would apply the distance formula between those 2 points. So that right there is the length of the median. And because I want to show that the centroid is 1/3 away from the base, what I will need to do is to verify the distance between the base and the centroid. So these are the 2 points that I will need to verify whether or not it is indeed 1/3 of the overall median. So I will need to now apply the distance formula between these 2 points. And the math looks really disgusting, but again, if you muscle through this, okay, we have these two fractions that we need to find the difference of. Create a common denominator, and we can then see, okay, that there's a common factor of 1/3 that I can factor out. And as it turns out, this expression, wasn't this the median? Right? So as it turns out, yes, it is true. The centroid is indeed 1/3 away from the 1/3 of a median away from the base. So by doing this, we've accomplished our proof. And just for completion here, we're going to do this for the vertex. We're going to find a distance that the centroid is away from the vertex. So to do that, we're going to apply again the distance formula between the centroid and the vertex. And then through some simplification, again, just like from the previous step, we can then verify that it is indeed 2/3 of the median. And that concludes the proof.